Okay, we're going to go ahead and get started. It's been a long time since I saw you guys. And you had that quiz over that long period of time. I guess most of you have already done it. I haven't actually looked to see if most of you have done it. It was just like 20 multiple choice questions that were basically the same sorts of things that have been on the exit tickets. Have you guys done it? Yeah, I'm guessing most of you have. If you haven't, remember, because I got it to you like a day later than I thought, or maybe even 2 days later than I thought, I gave you guys until tomorrow to get it done. Okay, if you haven't gotten it done, make sure you do. Okay, but pretty straightforward. Alright, as we move further into chapter 2, we're starting to get into the basics of what's going to be involved in calculus. And I used a terminology when we were introducing calculus a week ago that's going to come back, and we're going to need to dwell on this a little bit more. And it was this idea of the limit. Limit is going to turn out to be kind of a useful tool when we're doing calculus stuff, especially in terms of how we kind of derive what calculus stuff is for. We talked about limit the other day when, for example, we were trying to explain what we meant by a line, like the slope of some curve at some point here. Where we wanted to know like this line right here, but that we couldn't really figure out how to do, but we could figure out these secant lines really easily. We could find the slope of that secant line really easily, and well, if instead of being this far apart, if we chose this far apart, it was a better approximation to the real tangent line. And we could get closer and closer. The closer and closer we got those 2 points that were making that little secant line, the better and better the approximation got. We use the word limit to describe that. The limit as we got closer and closer to being those 2 points being on top of each other. But we want to understand the word limit in a more formal way, so that we can be using this in a mathematical way in our classes. I'm going to draw a couple functions up here. For example, here's a function. For example, here's a function. And for example, oh, I don't know, how about something like this? Here's a function. All happy functions may be drawn not so well. And the idea is, we should be able to talk about like, what is the value at some value of x, right? So like, what's the value of the function at some value of x? So like, if this is x, we have some value f of x here. And for a nice, smooth, continuous function like this, that's not a hard thing to think about. But what about at something like this, where there's some kind of discontinuity going on? Here at this value of x, like x equals 0 here, the value of f of x doesn't really make any sense. Despite the fact that very close to x, in fact, as close as you want to x, it does make sense. I mean, I don't know what f of x equals when x equals 0, but even a teensy bit more than 0, like x equals this place right here, which might be very, very small, I do have an idea of what f of x is equal to. There's just this place where it blows up. Or, well, like this one with this discontinuity in it. Now, we know how to read these symbols, right? The f of x, here's one function that makes it up. It's a piecewise function. It includes this value of x right here. And f of x. And then doesn't include this point, but then does include all this second function over here in this piecewise function. And that's good too. We know how to do that. But we could talk about this then in the context of what we call a limit. We could talk about like, here, let's instead of calling this x, let's call this a. We could talk about like the limit as x approaches a of our function f of x. Where we could say, as I get closer and closer and closer to x, what is the value of that f? I mean, as x gets closer and closer to a, what are we approaching? So, like for example, here, as x, if x was here, and then it was here, and then it was here, you can see how we're approaching this value. as we get closer and closer to this value, as x gets closer and closer to a, we're getting closer and closer to this value f of a. But that idea doesn't really work over here, because it kind of would matter what direction we're approaching it from. I mean, if x was over here, and we were getting closer and closer and closer to a, our value would be getting closer and closer to infinity. But if we were coming from the right side, and here was x, and it was getting closer and closer and closer to a, the value of f of x would be closer and closer to negative infinity. There's sort of two different ways to talk about the limit in this one. We could talk about the limit from the left and the limit from the right. And we actually have a notation for that. Like in this case, the limit as x approaches a, in this case a is 0, from the left is this negative sign, would be infinity. We're approaching as x gets closer and closer to 0 coming from the left. Is that the way the book uses the notation, or do they do it the other way around? Hold on. Hold on. I want to make sure I'm not telling you this wrong. Let's see here. Hold on. Let me look at an example real quick. As we approach -2, as we approach 1 from the left. Hold on just a second here. So I'm looking at this one here. Hold on. I just want to make sure I'm not telling you wrong. The book may have used the opposite notation. Hold on. So it's C. Hold on. Is the answer to CA, is it 3 or 6? 6. Okay, yes. So this means from the left. Yep, that's what I thought. Okay. It just spooked me all of a sudden. From the left. So as we approach this from the left, we're getting closer and closer to x. X is getting closer and closer to that a, in this case 0, but it's getting, the value of f of x is getting close to infinity. On the other hand, the limit as x approaches 0, and then they'll put a little positive sign there, that means from the right. So from the right means as we come, and x is out here, and we get closer and closer to the value of a, this is going to be negative infinity, as we're getting closer and closer. It might be easier to picture that on this weird one right here, where we got this weird stepwise function. Let's just say this one, here, let's say this value of a is 1. And let's say this is 3, and this is 6. So there's a function, f of x. That's this weird stepwise thing. But we could talk about it having a limit as x approached 1 from the left, or a limit as x approached 1 from the right. If we are approaching 1 from the left, here's x, here's x, here's x, right? X is getting closer and closer to 1. We're going to be getting our f of x being closer and closer to 3. On the other hand, if we're approaching from the left, from the right, here's x, here's x, here's x. These f of x's are getting closer and closer to this one, which is 6. This idea that as we sneak up, as x moves along on this function, as it sneaks up toward a value, well, if it's just a nice continuous function, nothing weird is going to happen. If it's just a nice continuous function, your answer is going to be whatever f of a, in this case, or f of 1 is. It's only going to be if there's like discontinuities or jumps in the function like this that we're going to have to be thinking about this, in more detail. Sometimes we write it as the limit from the left. Sometimes we write it as the limit from the right. As it happens, when we don't use that plus or that minus over here, it's just called the limit. The limit. And the limit from the left and the limit from the right don't have to be the same thing. Although often they are. I mean, clearly here, if we were coming from the left or from the right, we'd end up at the same place. There isn't always a limit. We'll see some examples in a little bit where the limit isn't defined. Alright, how would you find these things? If the problem said find the limit as x approaches 5 of f of x, where f of x is something, Well, okay, let's talk about this. One way to figure out if there is a limit and what that limit is what your book says, use a table. The book says just make yourself a table of values. Make a table of values, label one set of columns from the left, and label another set of columns from the right. Alright, let's say the function we're trying to evaluate is f of x equals 1 over x. And we're trying to find the limit of this as x approaches 0. It's going to look, well, something a bit like this. A graph of this thing is going to look something like this. And we want to know what its limits are. Because clearly at x equals 0, this whole thing blows up. And what they mean when they say make yourself a table is start with some value of x. Okay, we're from the left part of the table. And for each of those values of x, compute the value of f of x. And start with some number that's close, but not quite at where you want this limit, like at x equals 0. So maybe 0.1. Find the value of f of x when x equals 0.1. This happens to be equal to 10. Right, 1 over 0.1 is 10. And then they said, now get even closer to where you're going. If x is approaching 0, then take a big step closer. How about 0.01? We've gotten much closer now to x equals 0. And then compute f of x. That happens to be equal to 100. And then take another step closer. And compute its value of f of x. And do you see that there's a pattern emerging here? The closer and closer we get, not only is this blowing up, it's blowing up faster and faster. We're not approaching some value, we're approaching infinity the closer and closer we get. I'm sorry, this is supposed to be from the left. I'm going to put negative signs in front of all this. Sorry. Because we're coming from the left side. So we started off at negative 0.1, sorry, negative 0.1, and we came there. And then we put negative 0.01, and we got this. And 0.001, we got this. And we're finding out that we're not getting closer to some single value, we're blowing up. Then do the same thing on the right. Start with a number bigger than that value you're supposed to be approaching, maybe 0.1, and compute its f of x. And then do the same thing for closer. And then do the same thing for even closer. And then do the same thing for even closer. And again, you can see what's happening. The closer and closer we get to 0, now coming from the right, it's also blowing up, but in the opposite direction. It's blowing up towards positive infinity. This one was blowing up towards negative infinity. So on this problem, we would say that the limit as x approached 0 from the left of well, we can actually even write it out, of 1 over x was negative infinity. It approached negative infinity the closer and closer x approached to 0 from the left. We could do the same thing on the other side now. We could say that the limit as x approached 0 from the right of 1 over x equals positive infinity. And for that matter, remember, we can also just write the limit without that little plus or minus sign. That means both ways. If you come from the left and you come from the right, are you getting the same answer? The limit as x approaches 0 of 1 over x doesn't exist. You guys know that symbol? A backward E with a slash through it doesn't exist. There is no such thing. Because you get two different answers if you come from the left or you come from the right. But they're not all that horrible. I mean, how about, let's do the same sort of problem using a table, but now our function f of x will be, let's just say, 3x. A very simple function. Here, let's even draw its graph. And let's say we want to find the limit of this as x approaches 1. So as x approaches 1, we want to know the limit as we approach this point. And they want us to do it with a table, even though that's kind of stupid. So we make a table with one set of columns is from the left, and the other set of columns is from the right. As x, let's pick something close to 1. How about 1.9? Here's x. F of x. I'm sorry, not 1.9, 0.9. Sorry. We're close to, but not on, 1. Is that 2.7? I think it is. Now take a big step closer, like 0.99. .99 for x, plug that in, I think that's 2.97. Take another big step closer, 0.999. I think that is 2.9997. Do you see what's happening here? The closer and closer x gets to 1, f of x just gets closer and closer to 3. This isn't blowing up, it's coming to a nice value. So the limit as x approaches 1 of 3x, from the left anyway, is 3. Let's try it from the right. So we're going to start over here and get closer and closer here. So maybe on the right side, x, we'll start off with 1.1. Okay, we're close to but not quite at 1. F of x is 3 times that, so that's 3.3. Now let's take a big step closer to 1 from here. We're going to approach it. How about like that? Okay, we're 10 times closer. I think that is this one. Let's do it even 10 times closer yet. And you get even closer. Maybe be one more 0 in here. I'm not sure. I think it is. Nope, no it isn't. It's this one. Okay. But you can see what's happening. From the right, as we step closer, as x steps closer and closer to 1, f of x is just getting closer and closer to 3. So the limit as x approaches 1 from the right of the function 3x is also just 3. So we computed the limit from the left, and we computed the limit from the right, and they're both the same. When they are both the same, then we can just say that the limit as x approaches 1, not worrying about from the left or the right, is just 3. We went to a lot of work there. To show something that technically you could have just looked at the graph and seen it, right? There's nothing weird going on. Clearly, as we got x has got closer and closer to 1, f of x is just getting closer and closer to 3. In fact, any time that the graph is just a nice smooth thing that isn't doing anything wacky, like having jumps in it and stuff like that, these limits are always just going to be like the limit as x approaches, let's just say a, of f of x. It's just going to be f of a. It's just going to be whatever Like here, we were approaching 1. The function doesn't do anything weird. So the limit as it approaches 1 will just be f of 1. F of 1 was 3. They don't do anything weird. If the function isn't doing anything weird, the whole idea of limits is not hard. Okay? And in practice, most of the time what we're doing in calculus, the limit won't be hard because there won't be anything weird going on. The function will be nice and continuous and so on. But that's the kind of pain in the ass math textbooks are, that once they got themselves started talking about this, they had to dwell on the ones that are weird. Right? They have to start saying, all right, now make tables of, and here's some weird ones. And rather than me trying to draw a big ugly graph for you, let me fire this thing up and I'm just going to show you some examples of some weird ones. Did that turn on? Yeah. Let me just show you in your book. Zoom this thing out a little bit. Okay, so like for example, your book loves it when you're making these little tables to test a limit. This happens to be problem, I don't know which problem this is, 2.5? No, the table is 2.5. What is the name of this problem? 2.7 is the example number. And it's saying, here's a table to test the limits from the left and the right of this function that looks kind of harmless. F of x is sine of 1 over x. And they want you to approach 0 and they want you to find, let me write it down technically here, they want you to find the limit as x approaches 0 of the sine of 1 over x. Okay, it doesn't look that horrible. It looks like I'm approaching 0, so what I'm going to do is from the left, I'm going to start with a number close to 0, but less than. And then I'm going to take a step closer to 0, and a step closer to 0, and a step closer to 0, and I'm going to see what happens to f of x. And it's going to approach some value. Well, look, okay, here we are at 0.54, all right, and then 0.5 something or other, and then, okay, so maybe I'm thinking I'm getting closer and closer, the answer is going to be 0.5, but then look what happens if I get closer to 0. Negative 0.8. All right, get even closer to 0. 0.3, get even closer to 0. Negative 0.3, negative 0.03, get even closer to 0, 0.34. See, there's no pattern. We're not approaching any one value, as far as we can tell. It seems like there is no limit here. It's just sort of bouncing around. Let's try from the right. And they plug the same values in. Here we are close to, but a little bit more than what we're approaching, 0 in this case. And then we're going to step it closer, and then we're going to step it closer, and then we're going to step it closer. And again, when you plug that into f of x is sine of 1 over x, you just get a weird hodgepodge of numbers that don't seem to be getting closer to anything. It might be hard to imagine what that means until you actually look at the graph of the thing. What does the graph of sine of 1 over x look like? It's a mess. The closer and closer you get to 0, the faster the period of the sine wave is. And by the time you're getting in closer and closer to 0, the period is effectively infinitely short. The wavelength of these things is infinitely short. You're just zipping up and down. It looks so innocent. Sine of 1 over x did not look like it was going to break you. And yet its limit doesn't exist. There is no limit at f. Now don't get me wrong, at other points, right here, no sweat. The limit as x approaches, what would this be, negative 0.3? No problem. From the left, from the right, no problem. But here, things go to hell, right? There is no limit there. They're going to get excited about that kind of stuff. Okay? But fortunately, things like that aren't going to be the norm in calculus. We have to meet certain state goals and stuff like that we've done this assignment and so on. Here, let me switch you over here to show you this here. The actual goals here, they say we're going to use correct notation. We're going to estimate limits of graphs from tables of values. We're going to use correct notation. We're going to be using a table of values. We can look at a graph and estimate the limits. We can talk about the one-sided limits, which we did right from the start, about positive and negative from the left and from the right and so on. Talking about the limit between, okay, so those are called one-sided limits when we're coming from the left or from the right. A two-sided limit is when then, if the limit for the left and the limit for the right are the same, then you have a two-sided limit, okay? Most real limits that you use in calculus are two-sided, but of course, because math classes have to be a pain in the ass, the first time we talk about limits, they have all these examples where it doesn't work. Really, the only thing, infinite limits. Infinite limits, they just literally mean like the limit as x goes out just gets bigger and bigger. Which, there's certain functions where that will make sense, right? Like if a function does something like this. Well, the limit as it approaches infinity might be 0, right? The farther and farther you get out along the axis, that asymptotically is approaching some value. Okay, that's all that was. Okay, I mean, that's not really that hard of an idea. You guys know about asymptotes from like pre-calculus, right? That's the line that these things are approaching. Like over here, a vertical asymptote might be at x equals 0 or something like that. Places where it blows up. That's all they're going. To be honest, this first day of limits doesn't really freak me out. This first day of limits, we just do a couple of little examples, we build a couple little tables, or even just fill in some little tables, and we just start building this idea of something where these functions are just getting closer and closer to some place where we're not sure what the value is. Okay. In practicing calculus, it's not going to normally be something weird. It's going to be one of these well-behaved ones, more like this. But of course, in a math class, they have to first show us the weird ones. Okay? So I'm not terribly terrified of this particular assignment. I think you're going to be fine headed off to, actually here's the assignment right here. Page 154, 30 to 36 all. And then this longish list of odd-numbered ones. And again, it's okay if you don't do them all. If you're getting this, and I don't remember, like for example, 39 to 63, like is it 2 or 3 different groups of problems? Like these first ones are build a table. Well, if you built enough tables now you know how to do that, that's fine. Then skip to the ones, just make sure it says on the paper that you skipped. So I know you didn't just like stop. Okay? And now you're going to go to the ones that make graphs instead. That's cool. I'm okay with that. Alright? Alright, I'm not really anticipating this first day of thinking about limits as being such a scary thing. In general, I think, okay, here's the deal. There's a 500 level math class, theory of limits or something like that. They make an entire college course for like grad students about limits. Turns out there's all kinds of crazy things you can do with them. We ain't going anywhere near there. Okay, we're just going to be using them as a tool to understand calculus. Alright, that's all we need for that. I'm going to go ahead and stop the camera and get this thing started uploading for Jasmine, and I'll send it to Lisa since she's not here. And then, we can be, I also emailed you the exit ticket. I don't know, my server's giving me problems, so Melissa's bypassed doing the server thing. And just use the email on the exit ticket. Alright, yeah, Luke.
I did 2 exit tickets. I was